So I'd like to move to Earth, Venus, Earth, and to all of our work with some very interesting channels. So Pete has a lot of stuff to report over the past week, and I think Thomas does too. And so I'd like to turn the floor over to you both. So Thomas, so go ahead and tell us what's happened and what you might have planned over the next week, and anything that you need from us.
Yeah, so that's quite easy. Not a whole lot happened this week, so that's fast. We made the data available. That's kind of a milestone, and we will make that also known to the community. So you're free to do whatever you want with the data. There's a small example notebook just to show you how to read the data, how to correct it with the given Doppler offsets, and just to show you the peak. But I'm not in any way claiming that this is the best way of doing it. So it was not a joke when I said you should improve it. That was serious. For next week, I hope to make a start with figuring out actually fitting the numbers we have measured to the link budget. That would be interesting. I'm afraid we will not completely get there because we simply have more variables than we have data points. But at least it should give an indication on in which range things should be. So not much else. I will leave the floor to other people.
Okay, thank you. And for those of you watching and following along, the data that he's talking about is the data set, the recorded transmissions and reception from the Earth, Venus, Earth experiment on the 22nd of March. And so there's a data set from Dwingelo, and there's two data sets from Stockert. The reason why the difference is because of different antenna, essentially the antenna, different orientations and polarizations, with instructions on the included, on what to do with it. And thank you very much for the additional Jupyter Notebook or Jupyter Lab work, to kind of like, what do the corrections that you have to make have to do with Doppler. And that was plowed kind of into this with just the data and got pretty far, but the example notebook is super helpful. So what we're going to try to do is try to take the raw data and we're going to learn how to process it and then explain, what do you do with the data that you've generated? Continue working on the link budget and incorporate all that we've learned into that. And Thomas is exactly right. There's a lot of factors here. It's a complicated thing that we're doing. We'll just try to produce the absolute best document that we can. And one of the ways to kind of like increase the capability, the communications capability of this sort of very challenging channel, bouncing a signal off of a celestial body, so if you're familiar with Earth, Moon, Earth, where you bounce a signal off of the moon and receive it back at Earth, that's already hard enough. Now we're talking about Venus. And there are some techniques here. So we have lots available to us, from Zadov-Chu to delay Doppler channels. So I'd like to invite Pete to tell us a little bit about this and tell us what he's done over the past couple of weeks and what he's got planned for the near future.
Thanks. I'll share just 4 pictures. So first off, there's a lot of things we could do to make waveforms perform well for communication. FEC codes seem like one of the really fruitful areas. And I'll just admit right up front, this might be a less fruitful area, but it looks sort of interesting. And I'll share 4 pictures to show you why. So the root of this is, if you design an optimum matched filter receiver, be it a rake or whatever you like, its performance depends only on the waveform energy that you receive, not on the shape of the waveform. So if you look here, there's 2 examples on the top row and the bottom row. And in each case, we transmit a signal that has the same exact total energy on the left. So then that travels the channel, which is the same channel in each case. But of course, what you'll notice is, it's a really simple example, but the top result gives you an energy of 4, and the bottom result gives you an energy of 6. So that shows that if you design your transmit signal with channel knowledge, you can deliver better rake or matched filter performance simply because the received signal will have more energy than if you don't. So the way I got started on that very simple sketch was this. Back in March, Thomas sent 30 seconds worth of Zadov-Chu, and we received it and computed this cross ambiguity function. And so you see that the channel has, a curve in delay and Doppler. So our first simple example showed it just in delay, and this channel's in delay and Doppler. But the very same, I have two more pictures. The very same concept here in figure 2.2 extends to delay Doppler. So we could transmit 2 chips as an easy example, and we receive 4 chips, and the total energy is 4. So that is, indicates how the rate receiver match filter performance will be. It'll be, 4 times the energy of chip. But if we change that around and inform our transmitter design, and we send a delay Doppler optimized signal, now it's 6. So it's the same example again. We get 6 versus 4 when we design a waveform for the channel. And these are very simple, but I've started there, and it will probably take me another week or 2 to actually have a draft that's worth sharing. But the idea is then that theory builds towards this channel. And as I wrap up, I'll say what might be an April Fool's joke. There's really only 2 problems with designing an optimized waveform for moon bounce. Maybe there's only 2. So one of the problems is we see in the Doppler spread that the channel is only coherent for a half second, and the round trip time is 2.4 seconds. So we really are very unlikely to know the exact phase of these scatters. And of course, the cross ambiguity function surface, here we just show magnitude, but it has magnitude and phase. So probably the best hope is to use it non-coherently. And the other wrinkle I discovered was if you look at this curve, well, it moves a couple of hertz there in Doppler over, maybe like a few tenths of a millisecond. So if you think about that, the Doppler resolution of a few tenths of a millisecond is nowhere as good as a few hertz. So it takes a special approach to the waveform design in order to realize something that would take the benefit of the channel and make something that, the ultimate goal here, we're not rewriting matched filter theory. We're just trying to design a waveform that hopefully delivers more energy to the matched filter. So that's all I had.
Oh, well, that's kind of a lot. So I'll give the floor back to Thomas for him to comment.
Oh, I'm still trying to grasp this, so that's maybe also my goal for next week, to better understand on what Pete is achieving here.
Okay, yeah, we'll do our best to continue to try to communicate and explain and to make it accessible as possible. I think that probably the key concept here is that we've talked a little bit about the delay Doppler method of communication that has some promise, and I think something Pete raised was like, well, like if you approach this like classical terrestrial communication, you may not get the most energy back. Like if we can maximize the energy coming back, that feeds directly into better communications resolution. So if we can do that, if we can properly kind of identify that, and if it turns out to actually be solid and right, because we're going to double check and circle back and make sure that we got our fundamentals down. But what we're trying to do is try to get the most energy out of the signal as possible. Oh, go ahead, Pete.
Oh, I was just sharing kind of another plot, basically speaking to the point that you were saying, Michelle. So if you look here as another example a little bit later on, again, it's a draft, so things are a little bit rough shape. But if we just send a tone on the top line through a 4-tap delay Doppler channel, of course, we get 4 different tones on the right. And we would just make a rake receiver in delayed Doppler that would scoop those up. But if we send an LFM matched to a 4-tap channel, then you can see once again, it gets a lot more total energy just because it stacks up well. So it's extending that to the EME channel, I'll fully admit, has a couple of problems. And the round trip time being 2.4 seconds means any channel state information is always 2.4 seconds stale. So for that reason alone, this might be a really stupid idea, but giving it a go nonetheless.
Yeah, we'll give it a shot. And you kind of when we compare like the Earth, Venus, Earth efforts to EME, what the hope is that over the next 18 months till the next encounter with Venus, is that we can use EME in order to try out some of these ideas. And that may be possible, but we'll know more over the next week when we try to construct some signals and try to push this idea forward. And if not, then we'll just play around in math land and work over the next 18 months to try to have something and to try to prove it, like on paper, that this should work. So yeah, the basic idea is like, oh, okay, it doesn't look like we're collecting all of the energy that we can. And if we understand the channel and we look at the results that we've gotten from the 22nd of March, we can go, okay, yes, we got much more information about the channel, and then that informs the construction of a waveform. So what we'll do is commit to really trying to explain this in an accessible way, and to just to keep communicating why it's valuable, why it's a valuable approach. And anything that we find out that's kind of a negative result, like, oh, well, this seemed like it was a good idea at the time, but it's not, then we'll publish that too, because we don't want anybody to spend any time on things that don't work out for us. So that's
One question
summary.
on this, Pete. You mentioned the 2.4 seconds, but if we work between two different sites, we're not limited to the round trip time. So that should not be a limitation, right?
No, good point.
Oh, it wouldn't let me unmute. There I am. So the reason why it is true, it's just in slightly different terms. So if we send a probe to the moon, when it comes down to our station, it will be 1.2 seconds late. But if we could instantly optimize a waveform and send it back, it'll take 1.2 seconds to get back to the lunar surface. So we can't ever actually observe the lunar surface, create a waveform, and have it hit the lunar surface again, optimized in less than up and down from the lunar surface from our receive.
Yeah. I see. And even within that 2.4 seconds, things might change based on the geography and where it's reflecting and surface, etc.
Well, it might be. I'll share one other picture here quickly.
Actually,
This one.
that movie you made was also really nice.
Oh yeah. There's a movie too. I should have probably pulled that up. This one was just looking at a bunch of doing a low captures from March 3rd, and you see that a CW line was sent, and it came back with a median 3 dB width of 2 hertz and a amplitude variation of 8.5. So based on that, it spread the line about 2 hertz. Seems like the channel probably creates new realizations about every half second. Just guessing. So then if you think about the up and down time to get a signal optimized for the lunar surface, it probably innovates the channel about 4 or 5 times. And for that reason, I really don't expect that the coherent stuff is going to be practical at all. Maybe, but probably not. But in order to write the theory and work it out, starting from match filters and rakes, I decided to just break it down to the very simple thing and then build it back up into the tricky thing and see where it goes. So
Yeah, so this somewhat non-intuitive? Like when people talk about EME and they're talking about a gravitationally locked, planet or moon, that it doesn't rotate. So like, it should be really, really super stable, but it looks like it's not. Is that kind of in the ballpark of what you're saying?
Well, I mean, there's the main thing going on seems to be this vibration effect, and Dr. John Evans documented that back in his early papers, and he has a rotational rate on it that it varies between, and sometimes it's a little more, sometimes it's a little less.
Oh, it's
So
not the same.
It's probably the dominant source. But if you look in how Joe Taylor derived his modes for EME, they have really similar numbers, like 2 hertz at 1296 a Doppler spread. And sometimes it can be more, sometimes less. But I think this observation from March 3rd is pretty typical for 1296.
Okay. Yeah, it's not something that I knew, not being an EME uh, operator. This is really interesting because I think that the assumption is that oh, the moon is not rotating, but it is, and the libration actually is a factor in visual observation because there's a target list for visual observers in astronomy of the moon, and number 50, the hardest one to get, is a feature that's only visible at certain times because it's right on the limb, and it's only visible. Because of libration. So it's a significant enough factor to even enter into visual observation of the moon. So when I think about it, it's really not that surprising that we have this factor here. And yeah, this actually does affect the coherent modes quite a bit, like you said.
But we'll see where it goes. Like I say, it has some obvious problems and drawbacks in the road ahead. But given another couple of weeks, I think I can have it broken down to the basic theory and all, pin reference to um, venerated textbooks and things like that, and have it not be too weird science, but real engineering. And it may just be that at the end of the day that it gathers up a little more energy, but not a lot.
Okay. Yeah, thank you so much for all this work. It's really quite quite remarkable, and opens up whole new worlds. So we'll just keep plugging away. So Pete or Thomas, is there anything that we can provide or anything that you need over the next week or so?
Not that I know of, sorry. No.
Okay, yeah, just get in touch if there's anything that we can do to help. And thank you very much for the time spent on this, because this is hard work. Things through things worth doing are never easy. This is certainly in that category, and I think all that we're doing will help October 2026 be very successful. So I think we'll be able to do some very surprising things if all this pans out. Okay, so Rick, you have the floor if you like. Rick is a board member of DSES. They were involved in the Earth Venus Earth effort. And yeah, so you have the floor for anything for the FPGA meeting.
Thank you. First of all, I went down to the site at Haswell on Saturday, towing my trailer that's almost bigger than my truck. And I delivered a couple of HF beams that have been sitting in my barn for 2 years, waiting to be delivered down there. Well, while we were down there, we made repairs to the water system. They ran out of water during the EVE tests. Now, why do you need water? Well, toilets and ditches, things. So they had a bit of a problem. In any case, we had a meeting yesterday, and the project manager, our project manager for EVE, has been tasked to write up a preliminary report. Preliminary because we are not even close to done. We are committed to continuing study so that when the opportunity arises again, we'll be able to do a better job. I've talked to the science crew. We have quite a difference of point of view between our ham radio contingent and our science contingent on how this should have been done and how it should be done in the future. And we would like to bring our architecture and data collection more in line with what Thomas was doing. We have all the same equipment that Thomas and the other crews had. And so what we're looking to do, at Thomas's suggestion, in fact, is to, as best we can, simulate the EVE experiment to some degree with moon bounce using very low power to try to get link budgets that are not all that different than what EVE was. Now, obviously, Doppler and Doppler spreading and things will be different, but we know what they're going to be. So if we architect this correctly, we should see what we predict, as Thomas did in his EME experiments. So we have a couple of ways to do that. One is take 60-foot dish and transmit like milliwatts. That's probably not going to work in the short term because we're going to change the feed to 1.6 gigahertz for pulsar, magnetar, and other work. We're also going to do some hydrogen line scans and a lot of experiments we're going to be doing that don't allow me to transmit at 12 in the 1200 or 2400 megahertz bands. So one thought is I have Ray's, at Ray's house, he has a 3-meter dish, and he's volunteered to take that down and give it to me for this set of experiments, which I can run remotely, or I can drive over to his house. His house is much closer. It's a half hour instead of 2.5 hours each way. And it can be run remotely. So I'm hoping to do something that might benefit from your expertise in link budgets to help me, if we use the different antenna, what transmit power and receive capabilities should I try to set up to best simulate the 60-foot dish into Venus. So we might want to put together a new link budget to do a backwards link budget. Tell me what I should be transmitting to get the same signal to noise performance.
Okay, yeah, that makes sense. The way that we constructed the document or the link budget that we're working on is that each site has its own data class, and then the data class is just plugged into the rest of the calculations. And so as long as that data class, as long as that site can provide enough information, like the diameter of the dish, the power of the transmitter, noise temperature of the LNA, that sort of thing. As long as those things are there or they're known or can be measured or estimated, then we're good. It's done. So we have a similar request from JAMSAT because there's a 7-meter dish in Japan from an EME enthusiast that I know that is really interested in trying this stuff out to sort of help out to experiment over the next 18 months with EME. And that will be adding the data class there. And, to be honest, Thomas's link budget includes multiple sites, and all you got to do is provide, your location and basics of that. So I think you're in really good shape in terms of being able to predict give you an expectation or to give you information about in terms of link budget. We'll just keep working really hard. So, if you look at the link budget that we have at ORI and you look at the data class section, and if you can provide the information there, then it just plugs right in, and you get all the answers and visualizations. And same thing for what Thomas has done. So, in other words, yeah, I think we're good.
And the other thing we would like to do, and I'm not quite sure the best way to approach it at the moment because of all the conflicting needs we have for the 60-foot dish. I would like to better characterize the 60-foot dish in terms of TSIS and roughness of the surface,
Yeah,
and capabilities for higher frequencies.
right.
We have some stuff laying around out there that can help us do that, but we also have a desire to do, in addition to pulsars and magnetars, we want to do approximately 5 or 6 month long scintillation test with pulsars. We also have a scintillation test ongoing with University of Texas on site using GPS. And we have about 5 other projects, including Jovian projects and putting the 30-foot dish back up and putting the interferometry dishes back up. One of them blew over in a windstorm, so we have to get more concrete.
Right.
Don't underestimate how much concrete you need when you're out in the high plains of Colorado.
That's right. All you got to do is look around. Yeah,
Yeah.
any of the sites that you have can be its own data class and plug right in. So, I
Good.
I
So
understand very much that the big dish has lots of demands. This is like any telescope, any radio telescope, any place. It has a diverse set of, missions and feeds are going to get swapped out. Things are going to happen. So I think it's really wise to kind of look around and say, is there some evasive action to be taken that we can pick another dish and do some of this work, and if we have to use the moon as a target, that's fine. We'll just keep at it and keep plugging away. So everything that you've talked about here, I think we can help with if DSS is interested in working with us and continuing over the next 18 months. So it sounds like that's the case.
definitely the case.
Okay.
And I will be in touch offline with specific things that I might like to coordinate with you about as I get closer to trying to set up some experiments.
Okay, cool. Yeah, we're in it for the long haul, and this is interesting work, and we'll just we'll keep the lines open, and that's good to hear. All right, anything else before we close? Any last comments or anything from Rick? Anything else you want to report or need? Okay. Well, thank you, everybody. I know that time once you spend it is gone forever. So time that you spend with us and working on things that we do is truly priceless. It's deeply appreciated, and we, on behalf of ORI and the rest of the board, we endeavor to make your time really worth it, and to make sure that your work is published and gets seen and reviewed and is useful. This is meaningful work that we do. It's difficult stuff, ambitious stuff, and we could not do it without all of our volunteers and all the folks supporting us. So thank you very much. And for those of you that are on Slack, we'll see you there. And if you're not on Slack, just let us know and you can join. That's where the daily engineering happens. We'll be having, like I mentioned about the newsletter, we'll have our March newsletter coming out really soon with a lot of this stuff in it. So look for that. All right. Thanks, everybody, and see you next week.
Yeah. Thank you. Goodbye.
You bet.